Let's start. So a couple of announcements. Online homework 4 is due today. Hopefully most of you have finished it before the midterm. And I see many of you still survived, which is good to know. Homework 3 was supposed to be released today, but we are delaying it a little bit, both the release and the due date. We are still working on exactly when it will be out and due and so on. So just look for an update on Piazza. Okay? It won't be going out today though. So you have some more time to relax and work on your project. Okay? All right. So let's go back to non-parametric methods. We were talking last time about kernel density estimation, right? So we said, well, we just have some points, and an example would be a 1D set of points which are drawn here. So there's more of them here than over here, and so on. And we want to estimate what's the density of these points, right? Just to come up with an estimate for that. We talked about one way to do it, which was using histograms, where we took our feature values. So in the case of 1D, it's just we gridded up the feature values in bins, and we just output the average on each bin, right? Or by average, I mean like the count of how many points fall in that bin divided by the total number of points. So it's a relative frequency estimate, and that's a good estimate for your underlying density, right? So that's one way to do it. And then we also talked about the role that the bandwidth plays, right? So a larger bandwidth leads to dash bias, lower or higher. If I use a larger bandwidth, bin width, you can think of it as bin width here. A larger bin width means I'm chunking it up into larger and larger bins. Do you expect that to have more bias or less bias? More bias, right? And less variance, of course. So they go hand in hand in the sense of going opposite hand in hand, right? So bias is larger, but variance is smaller when you have large bins, and vice versa. So you want to choose the number of bins to be just the right amount. And we won't talk about that, like what the right amount is, except that you choose it by a balance between bias and variance, which can be done either by direct cross-validation, or you can, since you're going to use the density estimate as a plug-in into some classification problem, you can do always the test. You can look at the test error on some held out data set for classification as well. But it turns out that the optimal bandwidth needs to be chosen as a function of the number of data points. So how many bins you have. And again, in this class, we won't go into the analysis of how the bin width should scale with number of data points. But if you take 702, for example, statistical learning theory, then you will see that this bandwidth indeed needs to change with the number of data points. And that's what makes this method non-parametric, right? In the sense that the number of parameters, which are the number of bins here, need to increase with the number of data points. And that's why it's a non-parametric method, right? Whereas typically if you're doing you're estimating a Gaussian distribution or Bernoulli or binomial, those parameters don't change with the number of data points. Okay, so we talked about the histogram estimate, and we said, well, it tends to be blocky, right? So you can see the estimate built up here. And clearly, because you define these bins, it's very, very blocky. But there's an easy way around it, which is that instead of fixing the partition, we use, into a certain number of bins, we use a moving window to do the binning, which means that we start with, say you choose a certain bin width delta. Here also we choose a bin width delta. We take a region of bin width delta around the point of interest. So if we want to estimate the density at x, we'll put, this is the point x, we'll put a bin of width delta around it. So minus delta by 2 to delta by 2 around it. And then we'll just count how many training points lie in that bin divided by n. And so it's again a relative frequency estimate, except that the bin is now moving as you along with your point x. So it's instead of being pre-specified into non-overlapping partitions. So these bins can now be overlapping, right? And that leads to a somewhat, it at least gets rid of the blocky artifact here. It gives you a much smoother estimate. And this is actually an example of a kernel density estimate, right? So you can think of this term in here, which is computing whether or not a training point falls within delta of your test point little x. You can think of this as a kernel, right? It's a kernel which is outputting either a 1 or a 0 based off of whether your training point is within delta of little x or not. So what we can do is define it more generally by replacing this whole thing by a kernel which measures how similar xj and little x are, how similar a training point and a test point are. And that's what will give us this expression, which has this kernel, which measures how close xj and x are. And in fact, this is still a measure of similarity. That's why it's still called a kernel, even though it's slightly different. The requirements on this kernel are different than what you would have in SVMs. For example, because you're estimating a density here, you want all your kernels to be positive, strictly positive value everywhere. And we use this delta as bin width. We still want to keep that notion intact. So for example, we can define the boxcar kernel to be just this. It's indicator between -1 and 1, it's +1 and 0 elsewhere. But then if I'm using it around any point, I just, right? So if I write, so this is k of x. And because I'm writing k of xj minus x over delta, I'm essentially shifting it to be centered at one of the points and a delta region around it, right? And so delta, this -1 to 1 now becomes minus delta to delta. I've rescaled it's as if you took this kernel, you rescale the axes by 1 over delta. So now it's supported over minus delta to delta and shifted it by, say, xj, right? So that's how you can think of this. So boxcar kernel being a special case of this, but then you can have other kernels. You have looked at the Gaussian kernel before, so we can use a Gaussian kernel here as well. And again, this is the kernel when defined as centered at 0 and with a default variance of 1. But then when we plug it in here, we want to compute how far a point is from xj is from x. So we can center it at xj and use a bin width of delta. So we are again scaling it up and shifting it. So that's what this kernel, that's why you typically see these kernels written like that, the ones using kernel density estimate. They are recentered and scaled. All right. And it's equivalent. You can think of these kernels as either being centered at xj or x, right? They, as you can see from the expressions, it's equivalent to think of it as either way, right? Because you're just measuring are the 2 points within delta or not in some sense. So here's another and a very nice intuitive way to think of kernel density estimation. It's as follows, that you imagine that here are your points, right? These are your training points. And you have to come up with the density estimate at any other point x, here, here, wherever you can place it along this line, right? So one way to get at that is you place your kernel centered at each of your training points. So at each training point, you have your kernel. You center it along that. And all you have to do is once you have placed these bumps, so I have one bump placed around -2.1, another bump placed around -1.3. So these are all my training points. You have one bump around each training point, and then you just add them up. That gives you this blue line, and that gives you p hat of x for any x you choose. So it's a very nice intuitive way to think of it, that all you're doing is essentially wherever there is more training points, there's higher density. So you're putting more bumps there, and then when you add up, you get a larger density estimate, which makes sort of intuitive sense, right? And if you don't have as many points in some region, you are placing only very few bumps, and you get a lower density estimate. So it's a very nice intuitive way to think of this. All right. And we talked about before, these were two examples of kernels. More generally, you can use any kernel function that satisfies the following two requirements for density estimation. It has to be positive because you want your density estimate to be positive, and it has to integrate to 1, which implies that your corresponding density estimator is a valid density function. It also sums, if you take the probability corresponding to it, it sums to 1, or it integrates to 1. Yeah, so how would you compare different kernels? So for example, the boxcar kernel and the Gaussian kernel. The nice thing about the boxcar kernel is that it has finite support. So when you're doing the estimation, you only need some local points to compute the estimate. Whereas Gaussian kernel, whatever point you're trying to do the prediction, it involves the kernel for all of your training points, right? So you have to sum across all of you have to load all of your training points into memory, for example, if you want to do the prediction. But it leads us to a smoother estimate because the kernel itself is smooth. So imagine you are summing up a bunch of such box bumps versus Gaussian bumps, you tend to get a smoother estimate here. So it's still used widely in practice, though of course there's a trade-off between do you want more smoothness or do you want easy computability, right? So between finite support and infinite support. And here's again reflecting sort of on this choice of the kernel bin width, or in this case we call it bandwidth, once you have translated it to a kernel. This is an example from Larry Wasserman, who's a professor in statistics here. His book, All of Non-Parametric Statistics, which is a nice example of what he calls this Bart-Simpson density. It looks like the here of Bart-Simpson. So here's the true density he generated, which is indeed Bart-Simpson's head. And here's an under-smooth version, which means you use a very small bandwidth. And if it's just right, you get a good estimate. And if you over-smooth, you get maybe Maggie's head or something instead of Bart's. So again, the bandwidth plays the same role as bin width that we were talking about earlier. And you want to pick it again just right to get a good estimate, as you can see here. Again, higher bias here, but lower variance. And here you can already see it's very, very wiggly. So it's going to, as you change your data points, it's going to wiggle around a lot. So you'll have high variance with lower bias. All right, so let's compare histograms and kernel density estimates once again. So here's another example. This is the figure we had earlier when we were talking about histograms. And if we do kernel density estimation on the same data, and we used now this bandwidth, which actually I think this was done using Gaussian kernels. So H is the bandwidth of the Gaussian. And you vary it, you see that you get, it's like similar in the sense of being jagged initially, and then you get smoother and smoother estimates, not the blocky ones as you get here. But everything is the same in terms of bias variance trade-off and picking the bandwidth or bin width. All right. OK, so we have talked about these two, histograms and kernel density estimates. Let's talk about one other way you can possibly think of doing density estimation, which is also non-parametric, which is k nearest neighbor density estimation. Okay. So what's the idea here? Well, histograms, we fix the bins, and we just counted what's the relative fraction of points that fall in each bin. The kernel density estimate, we did the same thing, except that now the bin was centered at x. That's one way to think of it. And we count how many points lie within a certain distance of x, divide by the total number of points. And of course, you're dividing by delta, because you don't want to estimate probability distribution or probability values, but densities, right? Now, another way you can think of this is, how about if instead I fix delta? Right? Or sorry, in all of these, what you're doing is you're fixing delta and estimating the number of points. What if you say, well, let me fix the number of points and see what's the corresponding delta? So what do we mean by that? We fix how many training points we want around a test point, okay, that we will account into our density estimator, or that will add their bumps off. But then we say, how far do we have to go out to ensure we have that many points around the test point? Okay, and that gives us a k nearest neighbor density estimate. All right, so what's that? If we are going to fix now nx, right? So instead of fixing delta and counting how many points lie within delta of x, we are going to fix this number of nearest neighbors, which is k, and we are going to estimate delta from the data, which would be the volume in higher dimensions. It would be the volume of the ball that you need to go reach out to until you have k training points enclosed around your test point. Right? And that gives you the k nearest neighbor density estimate, right? Of course, computing this volume is hard, right? And also, actually, if you see in practice, oh, I think did I have an expression? Yeah, so you can see it right here. You're always using k. So instead of the number of data point or number of training points around x varying, now you fix that at k and you're changing delta, right? So, but yeah, here's how it looks in practice. And as you can see, it's not particularly appealing. So what happens is when you're trying to estimate these volumes, if you have very high density regions, then points lie very, very close to each other. So the volumes tend to be very, very small. And that's what, because you're dividing by the volume, you get very large estimates. So typically, k nearest neighbor density estimation is not as popular, because for density estimation, it leads to these spiked estimates, which is not very useful. But the reason I talked about this is because you can actually use this in classification, and then you actually don't have to estimate these volumes, and you get a very nice classifier out of it. All right? So let's look at that. But any questions on this before we move? Yes?
You mentioned you have to compute, you have like infinite support for the Gaussian.
Mm-hmm.
It seems like it gets very, very small at a certain point.
Right.
I'm assuming are there some kind of like implementation detail that you just like chop down at certain points?
Yeah. So yeah, in practice, people do all those sorts of things where you ignore beyond a certain threshold. So yeah.
Yeah, good. People will use KD tree type things to try and quickly get rid of points that are so far away they contribute very little, or something like locality sensitive hashing, also to throw points away that aren't going to have a big contribution.
Yeah, because otherwise you could never use the Gaussian kernel in practice, right? It seems like.
So this is interesting in that it looks like the density doesn't integrate to 1, right? Like the blue density is everywhere above the green density.
Right, yeah.
So that's
yeah.
another reason for lack of popularity.
Exactly, yeah, yeah. It's not even integrating to 1, right? It's positive, but it's not integrating to 1, as you can see clearly, because the green curve integrates to 1. Yeah, that's a good point. Yeah, so it's very, very spiky, and it's really because your volume estimates sort of tend to be very small when points get really close to each other in highly dense regions. And so yeah, so it's not popular for density estimation, but let's go to classification. Okay, and you'll see what pops out of a KNN, of plugging in a KNN density estimate over there. All right, so what is the KNN classifier? First, let me mention it because it's such a simple concept, and then we'll see how it arises from KNN density estimation. So say you have data from so these are documents, let's say, from 3 different topics, and you want to classify a new document. If I give you what should be its class, say it was here, right? And a very simple estimator you can, or classifier you can think of is, here's your test document, let's say, and we are going to use, say, k equal to 5. So we'll include 5 of its nearest neighbors, nearest documents that are most similar looking. And what should we do? So you have to come up with a label for this new point. We did something in kernel density estimate. We sort of added them together, right? Added the effect. We counted how many there are that are near. So we were adding them. Here, what would you do? You don't need to. You don't want to add them definitely to get a label. Yeah. So the most natural thing that seems to be, let's take a majority vote, right? I mean, of course, I put the test point at a cryptic location so that you wouldn't guess it as, I mean, I think it should have been easier here actually, but say it was over here, yeah, you clearly get you get the class to be whatever it is, sports over here. And even if you are close to the boundary, you're still taking majority vote seems to be the most sense, right? Is it on this side of the boundary or that side? It seems like majority is at least a good intuitive thing. And we'll see that actually this is a very simple classifier. You pick a certain number of nearest neighbors and you do the majority vote. A very simple, very intuitive classifier. It will pop out as if we were trying to do KNN density estimation and plugging that in to our Bayes optimal classifier. So how does that work? Well, here's the optimal classifier, if you remember. The best classifier is simply given as outputting the label which has the largest probability given x, right? Or we can write it in this using Bayes rule as the class conditional density times the class prior, right? And let's plug in our KNN density estimate for the class conditional density. Right, we can do that. So class prior is just counting the relative frequency of how often that class appears. And instead of the density for each class, so for Gaussian naive Bayes, we assumed it was Gaussian, right? Now we are saying we won't buy into this parametric assumption. Let's plug in a non-parametric estimate. And KNN is one candidate. So we plug that in. And we see that here is what the KNN density estimate would look like. So notice that because it's conditioning on y, the expression changes slightly in the sense that we are talking about ky as being the number of training points of class y, right? So we want to ensure you plug in how many some ky number of training points of class y, and ny is also the total training points of class y. And you see how far do I have to go out until you get k nearest neighbors, right? That's what you plug into your volume. But because you are conditioning on y, you only put in the fraction of points that belong to class y in there, all right? And so let's plug this in, right? And of course, one constraint is that, which you know, that if you're expanding out until you have k training points, they will belong to one of the classes. So you know some y ky is k, right? And what would be a good estimate of p hat of y? How often the class appears? It's just ny, total number of training points from class y divided by the total number of points, right? So it's ny over n. Make sense? Right? So let's plug these two things in over there. When I multiply these two things, what do I get? Well, the ny's cancel out. I get ky over n times delta k comma x, right? And we are saying our rule is supposed to be pick the value of that quantity or the y which maximizes it, right? So what do we have? We have our classifier when we do this plug-in, f hat knn of x, sorry, not y, of x becomes our max y ky over n delta kx, right? What's the solution of this? We are saying which value of y maximizes this expression. I can just ignore the denominator, right? That doesn't depend on y at all. Because we are not saying what is the maximum value, we are saying which y maximizes it, right? So all we care about, this expression just becomes this is equal to argmax of ky, right? So we are saying that the value of y which maximizes it is the one which has the most number of labels from that point within your k guys. So you reach out to k guys and you're counting how many points from class y are there. You're doing that for every class, and you're picking the class which has the largest number of points around you. That's just majority vote, right? So the majority vote falls out very, very naturally by doing this KNN density estimate plugin. And you can see now this volume and every stuff doesn't even matter, right? So you don't need to compute that or estimate that in any way. All right, so here's going back to our example set. Here's the nearest neighbor classifier, and of course you're varying k. K is a parameter you get to choose. So k equal to 1. So this is your test point. You go out until you hit 1 point. And what's the majority vote amongst all those points? It's just red, right? What happens with k equal to 2? So you're including this yellow point and the red point now. You're sort of stuck, right? You can decide usually in favor of either one. You can break the tie randomly, but very often people actually don't use an even k for this reason because you need to break ties then. But you can do k equal to 3. And now you have 2 yellow points and 1 red point, and the label changes. Yeah.
Sorry, can you explain more? Would you ever do weighted majority vote where closer points have stronger votes?
So KNN does not do that. But yes, that's also done a lot in practice. In fact, you can use any notion of distance between points, right? So yeah, a weighted one would also make sense. But at least as far as like you take this optimal classifier, you're just plugging in KNN, or what pops out is that you don't need to do all that. All you need to do is just take majority vote. And the distance, the density is sort of automatically accounted for because you will have more points from that class within your nearest neighbors if that class was actually more dense over there, right? So that sort of naturally pops out. You don't need to do that in KNN. Right. Okay, so we can do so on. We can do 5 nearest neighbors, you can see, right? And then again, the label, actually that's one of the reasons I chose a test point near the boundary, because for points near the boundary, you see the label actually fluctuates quite a lot, right? So what is the right k to use? You can see that this k is very much similar to the bin width or the bandwidth we've been talking about, right? How far we reach out, the larger we make the bandwidth, the more bias we incur. So something similar here happens. The larger you make k, the smoother is your decision boundary, right? And as an extreme example, you can see, what if I set k to be equal to n, all of your training points? Then you get the same label for every point, right? So it's a very, very smooth decision boundary in that sense. Yeah, but in general, you can see that the larger we make k, the smoother is the boundary, and the predicted label is much more stable. So clearly in the k equal to n case, it's very, very stable label. We are always predicting whichever class is more likely. And the smaller k we can make k, the predicted label becomes more, it's more accurate, right, for the points, as you can see near the decision boundary. The smaller you make k, the better you're doing at the prediction. But your estimate tends to be much more unstable as before. So again, you have a bias variance story here, similar to density estimation. I'll show you some boundaries that you get with k nearest neighbor classifier. And actually the one corresponding to 1 nearest neighbor, and then you can also actually see the effect of this k. But before that, let's just look at 1 nearest neighbor classifier. And you can see, of course, the boundary is very jagged. And that sort of makes sense, right? We are talking about, say, this is a test point, and I'm using only 1 nearest neighbor. So you just map everything. You look at the perpendicular bisector essentially between those 2 points, right? And everything that's closer here, you map here. Everything that's close to the red point, you map over there. And then that changes as you move, right? You're talking about, as I go around, I'm mapping every test point to the nearest training point. That's what's going on with 1 nearest neighbor. So you can think of that in terms of a Voronoi diagram, if you're familiar with those. So Voronoi diagram is a partition of your space such that every point in a cell, so these things are called cells, Voronoi cells, everything in a Voronoi cell is closer to the point within that cell than to a point in another cell. Right? And that's really what's happening here. We are essentially drawing a Voronoi diagram around the training points and classifying data according to that with one nearest neighbor. Okay? And so the decision boundary is just tracking along some of these. Wherever the label changes, you're essentially tracking down the boundary of these Voronoi cells. Right. So here are some examples of, again, some data set I generated, and 1 nearest neighbor, 5 nearest neighbor, 9 nearest neighbor. And you can see that K kind of acts as a smoother, right? The boundary is a lot more wiggly here. It smooths out a little bit more as you go further. So you are sort of overfitting here, right? Clearly with 1 nearest neighbor, you are making the boundary, you're moving it around until you can, like you are just moving it enough so that, or you're moving it as much as as needed to get to the nearest point of that class, right? Whereas here you're allowing for some errors. You're trying to find a smooth version, even if you have to make some error. Here you're avoiding making any errors by mapping every point to the nearest training point. So you're overfitting in this case. All right, so let's look at a quick example. So here's running k-nearest neighbor for web classification. This was a data set consisting of 20 news groups, 20 different classes. You can see the classes over here. These are all like computer-related articles. These are recreational ones, science, different talk about religion and so on, politics, and then some miscellaneous ones. 18,000 or so documents, 60,000 words, and k-nearest neighbor classifier was used. The training and test set was randomly split 50-50%, and there were 10 runs that were done by doing this split 10 times, and we were reporting the average number of times you got it right. And here's what the results look like. So even though it's a very, very simple classifier, all you're doing is using a certain value of k, and you are just looking at if I look at 2 nearest neighbors, what's the majority label amongst those 2 nearest neighbors, or 4 or 6 or so on. And you get these plots, and you can see it's still such a simple classifier is performing pretty well. It's doing like almost getting 70 to 80% accuracy in terms of being able to classify these specific pairs of classes. Right? Okay, so any questions on this? And you can see why it's non-parametric, right? Why KNN classifier is non-parametric. The boundary now exactly depends on how many data points you have. It keeps changing as you add more data points, especially when you can see it with 1 nearest neighbor, right, for example. That should be very obvious. So for 1 nearest neighbor, it's very clear to see that the number of parameters you need to characterize that boundary is really scaling with number of data points. All right, so we can move on to regression, unless there are some questions on this. It was really a very small, simple concept. All right, so let's talk about regression. And essentially, again, the idea is something similar in the sense, so what did we do so far? We have been taking something, if you think about Gaussian naive-Bayes classifier or logistic regression or any of these, you're assuming a global model for your distributions, right? And then computing whatever your classification boundary is. And what we did with these non-parametric approaches, in some sense, we are going local, right? You are only looking at nearest neighbors or points that fall within a bin or so on, right? And we are trying to work with those. So we can do something similar with regression, where say we are trying to sense the temperature. You can ask the question, what's the temperature in a room? And these are different sensors placed in the room. Then you would predict the average. But what if you have to predict say the temperature at a location? Then you would still want to do something local, right? So what would you do now? Here you just average all of your measurements. Here you are sort of going to do an average, but only over points that are within some radius around you, right? So here again, h is sort of like the bandwidth, and you're just counting, or you're averaging the y's, but weighted by this. You can think of that as a weight, whether you're near or not, right? So you're doing a local average now. And really, that's the idea we'll build on to do regression. Again, that we want to go local in some sense. So we'll call it kernel regression, or it's also known as local regression, and actually the particular version we'll talk about is Nadaraya-Watson kernel estimator. It's quite a mouthful, but all it's referring to is instead of taking the global average of your labels, you're just doing a weighted average, right? So what I showed you here is you can just think of these as weights, right? So the indicator xi minus x less than h divided by the numerator, that's wi. That's really just a weight you're giving to the ith data point, how far it is from you. And so our estimators will just be of this form. It's a weighted average. That's it. And we are going to weight each training point based on the distance to the test point. Right? So your weight could be, in general, so there I mentioned the boxcar kernel, which was saying 1 if you're near and 0 outside, but you can again put in any kernel as before. But now the weight, we actually want, because we are putting the weight is like a ratio of, right? You can see it from here. To make it local, you're doing indicator and over the sum of all of those. So you need to do something similar. So the bottom part sort of accounts for how dense the points are, right? And when you're doing the weighting. So you need to take the kernel value divided by the sum of the kernel value for all training points, and that gives you the weight for the corresponding point. And boxcar kernel yields the local average we just talked about, we said. So when you plug in this kernel as the weight, then what you get is actually called this Nadaraya-Watson kernel estimator. It's a weighted average, but where your weights come from a kernel. Okay? And once again, you can use the same kernels we talked about before. You can use the boxcar kernel or the Gaussian kernel. Okay? And what happens now is very, very similar, where now you can look at the choice of the kernel bandwidth. So this is again trying to predict some power versus multiples. Again, this is what you get with setting your bandwidth to 1. This is 10, 50, 200, very, very similar effect. Right? And one thing is actually for regression, the choice of the kernel tends to be not that important, but the bandwidth is really the important part. Actually, for all of these methods, I mean, the choice of bandwidth has some effect, as in how smooth your output is, right? Is it blocky or smooth? But the bandwidth is really what plays the major role in terms of deciding the performance. And requirements of the exact kernel are not that important. Okay, so let's look at this a little bit more formally. The kernel estimator we propose, just a weighted average, it has a nice connection to least squares that we talked about. Yeah, there's a question?
Can we go back to the previous slide?
Sure.
So what is the power here?
It's just something you're predicting. It's not power as in you're predicting power. You're regressing on power, like literal electricity power. Yeah, it's not power of a test or anything like that. Yeah. Yeah, it's just an example I again took from Larry's work. So yeah, don't interpret it in statistical terms necessarily. Yes.
So on the previous slide,
yeah.
Just can you actually implement this? So basically, at each point on the x-axis, you're sort of looking at an average of the values of the points around it.
Yes. Yeah. Exactly. You're just doing a weighted average. Of now, your points are like this, right? So earlier for density estimation, the points were right here. You're just estimating a density. Now you have a x and you have a corresponding y. Right? So you are averaging the y's. The weights come from how far the point is x and xi are. Yeah, so that's maybe switching from density estimation to regression could take a minute. So I hope everybody's on the same page. What's happening in regression is your training points look like there's a xi and a corresponding yi. So what's plotted here, you should think of it as yi. To do the prediction at any single point, you are averaging the yi's for the nearby regions, where nearby is specified by the weight. And the weight you get based off of how far a training point is from the test point. That constitutes the weight here. Right. Any other questions? Okay. All right. So yeah, so I was going to mention that kernel regression has this connection to least squares. And in fact, you can think of it as weighted least squares, where this wi is exactly the same weight we have been talking about before. So it's as if you remember least squares, you were trying to find a function f. In that case, you were looking at a linear function that minimizes just sum I equal to 1 to n of fxi minus yi squares, right? Now we have put in a weight for each training point, and the weight is as we just discussed, right? So it turns out that the kernel regression estimator we just talked about, that corresponds to choosing f of xi actually as a constant. So it's as if at every point you're trying to fit a local constant. You're not trying to do a global constant fit, but a local constant. So if we plug in f of xi equal to some constant beta here, and we solve for beta, you will see that the weighted average is what will pop out. Whereas you can try to do other fits, right? So earlier when we had done least squares, we had put in f of xi as xi times beta plus, or beta 1 plus beta 2. So a linear combination. You can also put that in here. That will give you a local linear fit. Right? So it's still going to be different than what we did before because of the wi's. So really the difference you should see is this, that say you have a bunch of data points. Earlier when you were doing linear regression, you were fitting a line, or say you did a constant fit, you were fitting a constant to all your data point together. Now we are doing it for around every data point. So now if I have x here, I'm going to do a linear fit here, here, whatever, depends on what kernel bandwidth you pick, but I'm going to do a linear fit, or I'm going to do a constant fit around every data point as I move. So that's the difference between just doing least squares estimate with a linear function or a constant, or you could do polynomial regression also, we talked about that. But there we were doing global fits using all of our data. Here we are doing locally around the test point. Does that make sense? Okay, so let's do that, at least for the constant case. We can plug in f of xi equal to beta here, and let's see what pops out. So let's do that. I put in f of xi equal to beta in this expression, and of course now I'm minimizing over beta, so that's, oops, wrong way. So that's the expression you get, right? And let's see for what value of beta is this minimized. One constraint you do have to keep in mind is that our weights satisfy something. The sum of the weights is, just from the expression you can see, right? If I sum over I all of the weights, wix, you get a 1, right? So all the weights have to sum to 1. So we are doing this constraint optimization kind of, right? But yeah, you do this. Actually, I think I have it written out. So this is our objective in beta. We are taking its derivative, setting it equal to 0 to find the minimizer. What's the derivative of this? With respect to beta, you get twice sum wi beta minus yi, right? And we're just going to set it equal to 0. It's really a simple derivation. And realizing the fact that, so I'll break it up into two terms, sum of wi times beta and sum of wi times yi, right? And I'm just equating the two. And of course, knowing the fact that sum I wi is 1, you get your solution, right? Because this equation is saying I need to have sum I wi beta equal to sum I wi yi, which implies that beta is sum I wi yi, right? Really, there's nothing much to derive here. So that's your weighted least squares output when you are doing a constant fit to your data. You can also try plugging in, again, f of xi as a linear term, xi beta plus beta naught, and see what pops out. That will be doing a local linear fit. Right? So yeah, in general, you can do any local polynomial regression, right? You can put in any number of terms here, polynomial of degree p. All right, any questions on this? Fairly straightforward, but I hope people see the difference from what we were doing earlier when we talked about linear or least squares regression, right? A global versus a local fit, that's really the difference. And again, what controls the bias variance trade-off here? It's also the fact that you are being local, right? So again, the bandwidth comes into play in addition to any polynomial powers you put in. In fact, you can show that even with just this constant fit, right? So the estimator, yeah, with just the constant fits, the sum I wi yi, that is itself a good estimator even for very complex functions. The reason being because you're choosing these weights, right, and the bandwidth. So you don't necessarily need higher powers to get a good approximation. But together, they both control the complexity of your classifiers. All right, so let me summarize the non-parametric methods we have discussed. In some sense, you can, and these are also called instance-based methods, because you're actually, when you're doing your prediction, you are actually going to load up all your, or whatever are the needed training points, and using those to do the prediction. You don't just have a set of parameters on which you base your estimate, right? You have to actually load your training points. And they're sort of, you can think of what is shared amongst all of these approaches we talked about. There's a notion of a distance, right, which the kernel requires. And you can, typically we use Euclidean, but you can use any other distance metric. There is a notion of how local you are, which is the number of nearest neighbors you choose, or the bin width, or the bandwidth that you choose. There's the weighting function, the kernel we talked about. And how do we fit the data points? So depending on whether we are doing density estimation, or classification, or regression, we could be doing any of these things, right? Majority vote, or averaging, whatever makes most sense. Weighted average, or polyfit. Okay. And again, something we discussed earlier, non-parametric methods, they require very mild assumptions on the data distribution. As we have seen, you're not really making any assumptions that it's Gaussian or anything like that. And they provide good models for complex data for these reasons. Parametric models tend to be very simple. Assume everything is like a blob, essentially, if you're doing Gaussian assumption. But of course, there's the trade-off in the sense that non-parametric models require storing and computing with the entire data set. So you often have to load your actual data sets into memory to be able to do that. And even though I said not histograms, there you have to still load up whatever is the estimate in each bin width, but really your number of bins is actually increasing with number of data points. So it's still pretty expensive. These tend to be much more expensive or data intensive than the parametric methods. And parametric models, of course, once fitted, they are much more efficient because you can only store the parameters, just use those for computation. Yeah.
So it seems like this kernel regression has no underlying model, really, of the data. Like when we did the nonlinear regression, you always had a model. Whereas here, there's nothing. Is that bad, or is it something we have to worry about? Is it overfitting if there's not even?
So what controls the what controls how complex it can be is your bandwidth here.
Right.
So because you're placing a bandwidth, you're still assuming something, but it's very, very mild. Essentially, what you're assuming is that your function is smooth. So it does not change very much as you go to your nearest neighbors. And there are formal ways to characterize it. If you take 702, you will see we'll be talking about Lipschitz or Holder continuous spaces. So all we are assuming is not that our function is linear or quadratic or something. We are assuming our function belongs to this very general class of functions which allows for all smooth functions that have one derivative or two derivatives or three derivatives and so on. So we'll be talking about essentially how well you can represent a function in terms of its Taylor expansion, or where you truncate the Taylor expansion. That's just a rough idea.
Yeah, it's similar in a lot of ways to when we moved from, let's say, the perceptron to the kernel perceptron, or the SVM to the kernel SVM, right? We went from a very restrictive assumption that we had a linear decision boundary to the assumption that we were just trying to learn a discriminant function that was smooth in the sense of having low norm in this function space. Right. And so, and then the nice thing is that you could trade off that norm against how much data you had. And so basically any discriminant function within a very large class could eventually be learned if you had enough data.
Right. And again, there also, like in some sense, the regularization would depend on how many data points you have. Do you want the data part to talk more, or the penalty part to, in some sense, talk more? And so those methods can also be thought of as non-parametric once you start setting the regularization parameter in terms of number of data points.
So this is all about prediction and very little about making a model, like a good model.
You can think of it that way, sure. Yeah. Yeah, the only reason I'm saying, like, it's not a model in the sense of a model, but you can still do things like density estimation, which is you're predicting with its density, right? Not necessarily a label. Yeah. All right, any other questions? Yeah.
So basically this KNN does not work well if there's a lot of features, right? Recursive dimensionalities, when you see high dimensions. The close points are less likely to find closer points, right?
Points are more spread out, right? Sure.
I was wondering, so in practice, how many features would you use KNN if
that's a good question.
So for density estimation, right, there is a very sharp drop-off in performance for functions in higher dimensions. And I would say for density estimation, more than like half a dozen dimensions, I would.
Yeah.
So I'd cut it off like, 5, 6 dimensions
points.
is the max that I'd try for a non-parametric density estimator. For classification, because it's okay if you get the density wrong so long as you get the class right, you're safer going up to larger data sets. I don't know. Do you
rule of thumb sort of is like around 10, but yeah, 5, 6 I think is probably more reasonable, that up to that many dimensions. Of course, unless so one thing you can capitalize on, which these methods don't right now, and there are, I think, still research going on how to do that, is suppose even if you're in high dimensions, your data often does not occupy all of the dimensions, right? So it's sparse in some way. Maybe it lies near a manifold. Then you can adapt all of these methods to take advantage of that. But that's a very, people are still working on how to make non-parametric methods take advantage of such low dimensionality. And yeah, then we get into some unfamiliar territory.
It varies from method to method. But for like the Parson window density estimate, that's probably the most constrained. I guess the histogram is the most constrained.
Yeah.
And then the Parson window density estimate. Maybe the least constrained of the ones that we just talked about is the locally weighted linear regression model. Because if you have a function that's close to linear, even in fairly high dimensions, right, you can afford to crank up the k and still get a pretty decent estimate.
Yeah, you could do a larger bandwidth in that case, right? Yeah, or a number of nearest neighbors. Yep. But yeah, again, these methods are data intensive, which can be interpreted as in high dimensions, you run into trouble. But yeah, I think it's an important and open direction on how can you, it's very easy to take any parametric method and have it do feature selection for you or exploit sparsity. How do you get that to work with non-parametric? I think people are still banging their heads against this problem. So yeah, if you want to try something out in your project, that will be something interesting to look at. All right, so unless there are any more questions, let me wrap up this part. So we talked about density estimation, in particular histograms and kernel density estimates. And I guess, again, the important takeaway is to understand the effect of this bin width or kernel bandwidth in terms of bias variance. We talked about k-nearest neighbor classifiers, how it leads to nonlinear decision boundaries. Actually, this is now a good time for us to think about what is the shape of different, of the decision boundaries that pop out of different classifiers. Right? So far you have seen a bunch of them, and you should be able to think of, in terms of regression, it's easy. We just see what you're fitting, right? But the same can be talked about how complex your model is in terms of the shape of the decision boundary. So we talked about Gaussian naive Bayes, and when it gives linear decision boundary, it can do more than linear, right? If people still remember that. When does it give linear decision boundary? You should be shouting out the answer back at us now.
When your covariance is circular?
Yeah, when your covariances are actually the same. They don't even have to be circular. But when they are same for both the classes, right? That's when you get a linear decision boundary. But in general, you can get a quadratic out of a Gaussian, right? So you can get either linear or quadratic decision boundaries from Gaussian naive Bayes. Logistic regression, at least if you don't kernelize, you're just getting a linear decision boundary. That's the form you have assumed, right? With different kernels, you can make it more complicated, or by putting in features that are nonlinear transformations, essentially. And with KNN classifiers, you can see that you can handle much, you can get more and more complex decision boundaries. But of course, again, the overfitting, you need to choose K correctly, otherwise you'll tend to overfit. So yeah, it's important to think of all these issues. And then we talked about the local kernel regression, right, which can be interpreted as this weighted least squares problem. And again, I think we should have, we will probably have a question in the homework. You get to play a little bit more with what the weighting means, how it's local versus global fits, and so on. Right. Okay, so I was going to do this in next class, but I think we went by fairly quickly. So we'll start a little bit talking about one idea that actually, I don't know if you thought about this when we're talking about all of these non-parametric methods, was we are not just done with non-parametric methods. One thing that pops out is all of these methods sort of assumed that we have the same bandwidth everywhere, or the same bin width, right, or the same number of nearest neighbors for every data point, which may be sensible but may not be, right? So what I call as spatially adaptive non-parametric methods actually gets us into the next sort of class of non-parametric methods, which are based off of what you might know as decision trees or regression trees in general. Right? So just to give you some flavor before we formally talk about decision trees. So this is not how decision trees were originally designed, but this is a nice way to think of them. is if you think about all of the local prediction, right? That's what this non-parametric estimation methods have been doing. Whether we talk about histograms, kernel density estimates, KNN classifiers, or this weighted least squares kernel regression, then they are essentially doing this, something like this. You have your data points, and say if you want to do classification, here's the true decision boundary, say from which these data points were sampled with some noise. And so basically the probability of label being green is higher here than here, but it's changing as you go near the decision boundary. Maybe they're mixing more and more. And what you're doing with these type of classifiers is, for example, you can build a classifier out of the histogram estimator also. We didn't talk about it, right? But you can just pin up your, like if you instead of plugging in the KNN density estimate into your optimal classifier, you can plug in the histogram density estimate. And you get a histogram classifier where all you're doing is you're again partitioning your space into bins, and then you're just counting. In density estimation, you would output the relative frequency, right, of the points within each bin. Here we'll output the majority vote within each bin, right? So we can just take the same idea, and you would get some estimator which looks like this. Now clearly you can see that this is not a very good estimate, not a very good classification, right? You're getting out of this histogram classifier. Instead, if you did what we'll talk about either today or next class, or decision trees, then you can get something like this. Okay, so what's happening here is that we now have a spatially adaptive partition. We are using smaller bins somewhere and larger bins elsewhere, right? And that can actually give us, as you can see now, the output is, so of course we have to figure out what size bins to use where, but if I told you that, what you're doing is now taking majority votes within these cells, and you can see that you get a much better approximation to your true decision boundary by doing that. Right? If I take majority vote over here, I'm not being masked out by this little noise here in terms of labels, whereas near the decision boundary I have smaller cells. So it sort of makes sense. Away from the decision boundary, we don't incur much bias by using larger cells because our label is actually uniform, right? Whereas near the decision boundary, we want to lower our bias by having smaller cells. So in some sense, what's going on is by changing the size of the cells, we are now lowering the bias we get in regions, or not lowering the bias remains the same. You're not affected much whether you use a smaller cell versus larger cell because it's essentially the same, but you're reducing the variance away from it, and you're still keeping a good bias near the decision regions. So you're doing a bias variance trade-off, but you're doing it spatially. In certain regions, you are using smaller cells to get a better bias. In other regions, you're using larger cells without incurring a bias penalty or lowering the variance by having more points. So that's one way to think of it. Okay? So we are somehow building, well, you can equivalently think of that as a tree, this spatially adapted partition, where you can think of a histogram as we dug down the tree and we had leaves at the very, very fine levels everywhere. We can prune some of these leaves, and we can come up with larger, and by pruning it means I'm just merging. So I take these 4 guys, which you can think of at 4 leaves, and I merge them into one block, right? So I prune the tree, corresponding tree, and that's how you would get something like this. So I've pruned this whole region. I end up removing all the leaves that would have come below this guy into one node, and similarly we are pruning at different levels in different parts of the tree, right? And that's how we'll actually end up with a decision tree classifier. Yes?
What's the advantage to pruning? Is it just an efficiency thing?
You actually get much better results. You can show that you actually get a better rate of convergence, if you want to talk more formally, with a decision tree than with a histogram classifier, essentially because of this idea that you can do a better bias variance trade-off by being spatially more intelligent about it. Yeah, so it has that advantage. And here's, like, again, another example of that's what your ideal classifier might look like. And you can use a decision tree to approximate the decision boundary, and you get something like this, whereas with the histogram, you get something like this. Of course, what's the right comparison? We are talking about the same number of cells in each partition. So there are 256 cells in this histogram partition. There are 256 leaves here in this tree, say number of partitions. But you see that because somewhere we go even finer than this, we are improving the bias near the decision boundary, and we are reducing the variance away from it. So that's why we get a much better overall error with decision trees than with the histogram classifiers in general. So again, before talking about decision classifiers, here's another example. This is one of my colleagues who had, one day thought of having a nice mustache and tried to do this. He was working on actually something with decision trees, ran decision trees on his picture in terms of actually trying to reconstruct the image. So all he's doing is just doing maybe some kind of, I think, literally averages within these bins. But again, you can see you don't just have to do classification. You can do sort of this averaging or compression with it, and you get a very poor reconstruction versus pretty decent reconstruction with using spatially adaptive partitions. And this idea of using adaptive partitions actually is being used. So if this is, I know this is old time for you, but if you look at JPEG 2000, that actually uses adaptive partitions. And before that, the JPEG used to use a non-adaptive partition, and so it would compress your image like this. That's why JPEG images were so much worse earlier. And after the 2000 standard was revised, they tend to be much more better. But it's essentially all based off of this idea of adaptive versus non-adaptive partitions. So yeah, we'll talk about, I think that's all I had here. I think I have my decision tree slides, hopefully. We can start with those. But over here, I think I still have them. But decision trees, the way we'll talk about them, were born a very different way. But I think that especially adaptive idea, so this is, I'm using it from earlier, is sort of, I think that's sort of nice because you can use it not just in decision trees, but all the way, as you saw, we can talk about coding, compressing different ways, or you can talk about regression in these different cells. Again, you can do majority votes, or you can do averages, or you can do fits of polynomials even. You can do whatever, but just that you're using a spatially adaptive partition. All right. So let's talk about decision trees because we still have about 20 minutes. We'll sort of do it the more machine learning-ish way, the way it's been conventionally done. But you'll see all the pruning-based stuff that I talked about pop up. All right. So first let's just start with what does a decision tree represent, right? And what I showed you earlier was more in a continuous kind of setting where I was saying you can divide things up and so on. But we can talk formally in terms of, like initially people started thinking of this more in like, I guess, a discrete setting way. By that I mean all your features are discrete. So here's an example of a decision tree on discrete variables. And what it looks like is essentially it's taking a bunch of features, right, and their values and splitting based off of, so every node represents a feature. Right? So this is actually data where, say, you are looking at people and representing them by features such as whether they got a refund last year or not, what's their marital status or their taxable income, and you're trying to predict whether they are going to cheat on their tax reform or not. Right? That's one example. But here your features are sort of discrete, or if they are not, which like taxable income, you can probably think of it as not discrete. We'll see how to handle that as well. But in general, decision trees can handle both discrete features or continuous features. And every node is going to represent a feature, right? So each internal node. And we are going to test on its values. What value does that feature take? And we are going to split. So each branch from a node selects one value. So in the discrete case, it's easy to understand. You're selecting either was the refund yes or no, and you're moving down based off of what those values were. And you keep on doing that. You go over all of your features. Sometimes you can reuse the features later on in the decision tree. Sometimes you cannot. That depends on the particular algorithm. And we'll talk about one specific one later on. Right now, it's just how to read a decision tree. So I gave you a decision tree. Every internal node represents a feature. Every branch represents values that the variable can take. For example, refund can take yes or no. So you can go down these two directions. Marital status can take maybe 3 values. And you can club some of them also. So if you're single or divorced, you go down this. Married, you go down this, and so on. And what the output or what the label represents, I should say what the leaf represents really, is the predicted value. Right? So at the leaf, you will have whether the cheat was a yes or a no. You have a rule for that. Okay. So what I've shown you so far is just given a decision tree, how do you read it? So if you want to figure out what's the given a decision tree, how do we assign label to a test point? So we haven't talked about learning. I haven't even told you about training data so far. right? How do you use training data to learn it? But given a decision tree, you know what it means. And now let's see, given a decision tree, how do we assign label to a test point, right? So what is a test point? Well, a test point is a person, so he has some value for different marital status or taxable income, and we actually want to say whether he's a cheat or not. Suppose we have trained a decision tree using some data given here. How do we output its label? Well, we just move down this decision tree. We start at the top, look at refund value for that person. It's no, so we move down this line, right? So we check down refund. We move down this line. Then we check our marital status. It's married. We go down here, and then we just output our label as no. So given a decision tree, it's very easy to say what your decision rule is going to be, right? And yeah, we'll talk about how to learn it, but before that, let me just say more generally, you can think of decision trees in the following way. You can think of them as splitting features that can be whatever. They can be discrete, they can be continuous, they can even be categorical. You can have things like one of the feature takes values A, B, C, or D, and you can group them by, you split on AB versus CD, and so on. So they are very, very general. Each internal node will always represent some, it can represent one feature, or it could even represent set of features. For example, here you could split down on x1 being this value and x2 being this value. You're splitting down on both simultaneously. It does not have to be a single feature at each node. And each branch from a node selects a set of values, right? So if it's binary variable, you can just split down on yes and no, or true and false. If it's categorical variable, you can split down on different categories, A, B versus C, D. If it's continuous, you split down on is it bigger than 0.25 or less than 0.25, for example. So you can define them in very, very general ways. And this is always true that at the leaf nodes, you always have a prediction for your y. So given any test point, whether whatever continuous or whatever features it has, there's a way to move down this decision tree by just following these arrows, and you can arrive at a decision rule. And what I'm showing here is again sort of the connection to what we talked about before. What you get is a spatially adaptive partition, right? So if I have just x1 and x2 as shown here, right, over here. So x1 could be continuous and x2 could be this A, B, C, or D. Then essentially, whether or not how deep my trees goes, if I list out all values, all variables, all features can take, then I'll end up with a histogram. I'm going all the way down, right? But it could be a pruned version, and then, for example, here I stop if x1 is, say, bigger than 0.5 and then x2 is A and B. I never check it further. Is it 0.25 or is it A or B, right? Okay. So, oops, this stopped working for some reason. I guess I ran out of battery. And this stopped responding. No, it's something else. Oh, it's my computer. I see the circle of death. So, okay, we'll wait for a bit. But okay, any questions so far as what a decision tree represents and how general it can be in terms of things it can handle, and how do we assign a label to a test point? I hope these are things everybody is comfortable with, right? So we are going to talk about learning a decision tree. Hopefully, if my computer comes back. Maybe not. Okay, so what we'll talk about next time is essentially taking a bunch of data points. So what would be a data points here? It would be a list of such, I don't think I can even go back, but it will be a list of people, right, from which we have collected the data, whether depending on what their taxable income was, their marital status was, and so on, did they cheat or not cheat in the past, right? So we have a bunch of such training points. We're going to use that. We're going to learn a rule, and there are lots of different algorithms because, as I said, there are much very general things that a decision tree can do. But we'll talk about a specific one. I think we'll talk about ID3, which is one particular algorithm that only allows you to split on one feature once. Okay, so you use a feature only once. In general, you can see as over here, you can repeat splitting on x1, for example, right? Whether it's bigger than 0.5 or not, and then whether it's bigger than 0.25 or not. But ID3 only allows you to go one feature at a time. And then how do we pick which value to split on? So we'll talk about things like information gain and so on. But I guess, yeah, I'll stop here because I think I should have some slides for that before I talk. All right, any questions? Otherwise, we'll just wrap up for today. Okay, good to go today.